Hello and welcome to another lecture of classical motion of a single particle. In this lecture, we simply continue our previous discussion on phase space and phase space trajectories, and finally, the concept which I introduced, that is the concept of fixed points. Okay. So, first we start with phase space trajectory. So, given the equation of a particle, let us say x double dot plus x is equal to 0. Okay. You can easily see that this is the equation of a simple harmonic oscillator. Okay. Or if the Lagrangian is given for that same particle, half x dot square minus half x square. You remember this type of things are actually already made in homogenizing those quantities. So, there is you should not really worry why x double dot is added to x, whether it has dimension of length by time square, and here this one has a dimension of just length. Okay. That is because there are some constants which are accordingly multiplied, so that they are actually brought into the same units. So, whenever even in the exams you see this type of question, do not get anxious that whether they are possible quantities or not. Okay. So, they are homogenized. Okay. So, in both cases you will have, okay, whether I give you directly this equation or you find from here by using Euler-Lagrange equation, you will find this equation. Now, if I tell that, okay, so what will be the phase space trajectory of such a particle? So, for that actually what is the formal method? We have to actually solve this equation to get or to obtain x as a function of t. Then once you get this, you just find x dot as a function of t, and then finally you actually can plot this in the phase space. Okay. And you can, so here let us say I can say it is x and it is x dot. Okay. You can plot that, and then you can say, okay, this is my phase space trajectory just for 1D motion. Okay. Now, here I am just trying to communicate one very important vocabulary. Whenever we are considering 1D motion in classical mechanics, okay, the phase space dimension is 2. When we are considering a motion with 2 degrees of freedom, then we are considering a phase space of dimension 4. So, whenever in the questions or even in the assignments we ask you to do some problems in a, let us say, 2D phase space, it does not say the motion is 2 dimensional, it simply says in the realm of classical mechanics the motion is actually 1 dimensional. Sometimes also in several books and problems you can see 2D flow. Flow is exactly has the same meaning as that of a phase space dimension. Okay. So, a 2D flow simply means that you have actually in reality a motion with 1 degree of freedom and 1 corresponding generalized velocity. Okay. For if I say a 4D flow, then actually it will correspond to a 2D motion or a motion with 2 degrees of freedom and 2 corresponding generalized velocities. Okay. Now, here I am talking of a 2D flow or 2D phase space. Okay. So, in general I have to do this, and then from that I can do this. Okay. But once again I have a shortcut method, and you will easily understand what is that, and that is simply when you have this equation, okay, you can actually write always x dot x double dot plus x dot x is equal to 0. So, you multiply x dot throughout, okay, with this equation, and then you actually write this is d dt of half x dot square plus half x square is equal to 0. So, then you have half x dot square plus half x square is equal to constant, let us say some I would call that capital E. Okay. Now, you can easily imagine what this is the total mechanical energy of this oscillator. Okay. Now, if you give me the value of E at one point immediately I can give you the phase space trajectory for that particle. Okay. So, that is sometimes a shortcut method using the invariance we can at least in one dimensional motion or in 2D flow or 2D phase space we can find the phase space trajectories. Okay. So, here you can see the phase space trajectory will simply be given by x dot square by 2e plus x square by 2e. Okay. So, that will be equal to 1. Okay. So, it is nothing but that you have x dot square plus x square is equal to 2e. So, I can 2e I can write as r square. So, this is nothing but the equation of a beautiful circle. Okay. So, here in this phase space it will be simply like this and it will have origin at the center. So, it will have like this. Okay. Now, if instead of just like this I had half m x dot square plus half k x square equal to e. Okay. Here I have made everything 1. Okay. That is why I have a circle. Then you will see that actually the thing is x dot square by 2e by m plus x square by 2e by k is 1, and since they are not in general necessarily not necessarily equal, this is the equation of an ellipse. Okay. This already I have discussed also in the framework of simple harmonic motion. Now, let us say I have another motion where the Lagrangian. So, let us consider the Lagrangian which is L equal to half m x dot square minus plus half k x square. Okay. So, for a simple harmonic oscillator we have a minus sign, here it is plus sign. Okay. Then you actually can easily show that Euler-Lagrange equation will lead m x double dot minus k x is equal to 0. Okay. And if it is the case, then you can actually write once again m v dv dx, because once again in 1D d2x dt2 is nothing but v dv dx, okay, is equal to kx, and then m v dv minus kx dx is equal to 0, and that is why finally you will have d of half m v square minus half k x square is equal to 0. Okay. V square means v is nothing but is equal to x dot. Okay. So, I can simply write v just x dot. Okay. Half m v square minus half k x square is equal to some constant. Okay. And from that again you can see that you will have v square by 2k by m minus x square by 2k by small k. Okay. This is actually small k. Okay. This is equal to 1, and you know, since they are not necessarily equal to each other, even they are equal to each other, no problem, actually the nature remains the same, they are representing a hyperbola. So, in the phase space they will have actually, so x and x dot. Okay. So, you can actually have x dot, you can actually have hyperbola like this, different type of hyperbola that will be given by the specific value of this constant k. Okay. So, which hyperbola will be exactly for one particle or for the motion of a specific system or specific particle, that will be given by this value of k, that whether this is this hyperbola or this hyperbola or this hyperbola like this. Okay. So, you see by this method we have found the phase space trajectories. Now, what to do for finding the fixed points and why also they are very interesting. Okay. So, a fixed point is something which is, so I am just now taking the special case. So, now concentrating on classical mechanical systems, actually more precisely with a single particle. Okay. That is the principal objective of this course. Okay. We know that x and v or x and x dot, whatever you think, in 2D phase space are the state variables, and the equations are given by x dot equal to v and v dot is given by is equal to some f, which can be a function of both x and v. Okay. So, here I am considering my assumption is to make the system autonomous, so that no explicit time dependence is presenting here, and we will only consider the autonomous systems for this course. Okay. So, if you have this, then at fixed point x dot equal to 0 and v dot equal to 0. So, you will see that since x dot equal to 0, v is always 0. Okay. So, v is 0 means if you just draw the phase space diagram, okay, just 2D phase space diagram. Okay. So, if you have x and x dot, the fixed points will always lie on these axis because its x dot is 0, okay, by construction. Now, for v dot is equal to 0, we have to actually say that this is also equal to 0, and for that we have to actually explicitly know the functional form of f as a function of x and v. Okay. So, I will just do one example. So, if I just take the motion of a single particle under, so the particle is moving under a potential u of x is equal to minus x square by 2 plus x to the 4 by 4, okay, and so the force which is acting on the particle will be given by simply minus du dx, which is nothing but x minus x cube. Okay. Now, we consider for simplicity the mass of the particle is equal to 1. Then what are the fixed point? Okay. So, we know the fixed point means that at fixed points x dot and v dot both are 0. Okay. The phase space evolution equations are, one is x dot equal to v, another is v dot equal to minus x, sorry, another is v dot is equal to x minus x cube. Okay. So, for fixed points v is equal to 0 and x minus x cube is equal to 0, and so x square minus 1 is also 0, and then x will be equal to 0 plus minus 1. So, you understand that you have 3 fixed points. Okay. They are the fixed points. Now, at this point I want to make one point very clear, that if you now simply say that x is equal to 0 plus minus 1, they are fixed points, that is actually partially correct. You have to say this and v is equal to 0, okay, because only when you specify both x and v, then only one point in phase space is well defined. Okay. So, what are actually the fixed points? So, the fixed points are 0 0 plus 1 0. So, you see that the fixed points means actually is a collection of x and v. So, v is 0 for all, and then minus 1 0. Okay. Now, I can actually go a little bit further and introduce the concept of somehow a concept analogous to the stability, just as we did for a potential, here also in the case of a fixed point, and actually in the neighborhood of a fixed point. Okay. We can actually think that a fixed point in which we will have, in the neighborhood of those fixed points, we will have some nature of the phase space trajectories which are not giving any instability, okay, then they are called stable fixed points. Okay. Now, we can be interested to know the nature of phase space trajectories in the neighborhood of each of the fixed points. Okay. Now, before going to that, try to understand what is the meaning of a fixed point. A fixed point actually is not just a point during the motion or during the evolution. Actually, if you really think, a fixed point is a point at which there is no further evolution possible. So, if you start the system, you prepare the system at the very beginning at a fixed point, the system will not evolve any longer. Okay. So, it is not that, for example, whenever a pendulum is moving, okay, in 2D space like this, okay, and then you know that at the two extrema the pendulum's velocity is actually 0, but its displacement is not 0. Here it has a non-zero velocity, but the displacement is 0. Okay. So, here whenever we are talking about the fixed points, if I now ask you that in this motion what is the fixed point, the answer is there is no fixed point. The motion associates a fixed point does not mean that a specific example of the motion actually associates a fixed point, because a fixed point is associated to the whole class of motion with different possible initial conditions. So, now let us say I am preparing this pendulum in such a way that I am giving it a non-zero velocity at this point. So, it will come here. I am giving a non-zero velocity here, it will come here. If I give a 0 velocity here, it will also come here. If I give 0 velocity here, it will come here. Okay. Now, if I give 0 velocity, but at this point it will never move. So, this creates the situation where the motion actually has reached or obtained its fixed point. Okay. So, a fixed point is not a point which is encountered during a motion, because once the fixed point is reached or once the fixed point is met, okay, there is no further evolution in phase space. Okay. So, you see that a fixed point actually for a simple harmonic oscillator, what is a fixed point? That is x is 0, x dot is 0, that means the total mechanical energy is 0. Let us say you prepare your oscillator with 0 mechanical energy, it will not move, that is the fixed point. Okay. So, this is the concept of fixed point. Now, we can actually, whenever we are talking about phase space trajectories in the neighborhood of each of the fixed point, actually we are thinking that if we know that all those combinations of velocity and position, they are giving us fixed points. So, if instead of giving exactly the fixed points, if initial conditions are given in a such a way that they are actually start from a point which is very close to the fixed point, but not exactly the fixed point, then what will be their motion? And with that motivation we do this study. Okay. So, for this system you have 3 fixed points, and I want to actually know what will be the phase space trajectory in the neighborhood of these 3. I first take this point 0 0. So, I know that the evolution equation in the phase space, they are given by this, okay, and in the neighborhood of 0 0, basically what happens, x dot you can write equal to v, but v dot you can practically write as x, as x cube is very less than x, okay, because x is very small. Okay. It is very close to 0 0 point, both x and v, they are very small. If you write that, so what is this? You can simply say, okay, then I can actually divide this thing by this one, and I will have v dot by x dot, which is nothing but x by v, and this is dv dx finally, because dt by dx dt is dv dx is equal to x by v. This is also another method by which you can find the phase space trajectories. Okay. So, you will have v dv is equal to x dx, and you will finally have that v square minus x square is equal to some constant. Okay. So, it will be a hyperbola. Okay. What happens in the vicinity of plus 1? So, in the neighborhood of 1 0, what happens there? Then of course, v is always very small because this is very close to 0, but x is very close to 1. So, x is not small, but I can now think that x can be written as some 1 plus very small quantity x prime. Now, that x prime is actually very small with respect to 1, and x prime actually can tends to 0 practically. Okay. So, and x dot is equal to x prime dot as well, okay, because this is just some constant shifted. Okay. So, what will be v dot V dot will be x minus x cube, which is now given by 1 plus x prime minus 1 plus x prime whole cube, and this x prime is very small with respect to 1. So, I can now do the expansion and I can have minus 1 plus 3 x prime, which is finally giving me minus 2 x prime. So, the set of equations is x dot is x prime dot equal to v and v dot is equal to minus 2 x prime. You can simply write, so dv dx, okay, will be equal to now, so v dot by x dot, and v dot is okay, but x dot is also you can write x prime dot, okay, and this is minus 2 x prime, that is by this, okay, and x dot prime is nothing but equal to v. Okay. If I do this, then I can also say that v dv will be equal to minus 2 x prime dx, and what is x prime? X prime is nothing but x minus 1 dx. Okay. So, I can finally write d of v square by 2 plus, now x minus 1 times dx. So, dx is also equal to d of x minus 1. So, you can write plus x minus 1, okay, square. Just a minute, let me just check. So, I have v square by 2, yeah, yes, I have this, yes, and then I have 0. Okay. So, v square by 2 plus x minus 1 square by 1 is equal to some constant, and then constant you just bring over here, and it will finally give you an ellipse. Okay. Okay. You can do the same exercise in the neighborhood of the other fixed point minus 1 and 0, and you can tell me how they are looking like. Okay. In the next lecture, I will try to make a bridge between this concept and also the concept of stability, okay, and thereby also discussing nature of different type of fixed points. Okay. Thank you very much.